There is a liquid that brings dead dirt back to life in 48 hours. It costs less than $1 to make. It fits in a jar on your kitchen counter, and university researchers have measured its microbial acceleration rate at 300% over conventional methods. No compost, no fertilizer, no chemical inputs, just rice water, milk, and 7 days of waiting. Soil that could not grow weeds is now feeding entire families, and the $300 fertilizer sitting on the shelf next to it is making the problem worse. 9,000 years ago, in the Yangtze River Valley of ancient China, farmers first domesticated rice, and almost immediately they noticed something that nobody wrote down for centuries but everybody knew. The water used to rinse rice, the cloudy, starchy liquid that most people poured away without thinking, made other plants grow stronger when it was discarded onto garden soil. This was not a controlled experiment, it was observation, the kind of observation that accumulates over generations until it becomes indistinguishable from instinct. Village elders in Korea watched animals thrive on fermented rice water runoff. They watched the manure from those animals create more vibrant soil. They watched that soil produce more abundant harvests, and they distilled what they saw into a single phrase that survived for 3,000 years. What feeds the pig feeds the soil. By the time Korean households had developed their deep culture of fermentation, turning cabbage into kimchi and soybeans into doenjang, the deliberate fermentation of a rice wash water had become a standard feature of agricultural life. The cloudy liquid called salduk was not wasted. It was cultivated, fed to livestock, poured onto fields, composted into the biological infrastructure of the farm. And then, in 1935, a boy named Cho Han-kyu was born into a farming family in Suwon, South Korea. He grew up watching Japanese industrial agriculture strip Korean soil of life through chemical dependence. He watched farmers become poorer as their soil became more degraded. He received conventional agricultural training, and then he rejected it entirely. By the 1960s, Cho had returned to his family farm with a mission: document the traditional Korean growing methods before they disappeared, systematize them, test them, and prove that the kitchen wisdom his grandparents had practiced was not superstition. It was science. What emerged from his work was Korean natural farming, and at its cornerstone was a preparation so simple, so cheap, and so biologically powerful that the agricultural chemical industry had every reason to ensure you never heard of it. Lactic acid bacteria serum, made from rice, wash water, and milk, brewed in a jar, applied at 1 part per thousand. In 1975, Cho applied it to a 2-hectare test plot of rice paddies that had been abandoned after chemical overuse had rendered them nearly sterile. Within 48 hours, visible microbial activity appeared in previously lifeless soil. After 30 days, soil structure and organic matter had measurably improved. By harvest, yields exceeded chemical plots by 40% with zero purchased inputs. The $300 fertilizer had failed those fields. The $1 liquid brought them back. Before we talk about how the liquid works, you need to understand what healthy soil actually is, because the entire industrial fertilizer model is built on a misunderstanding so fundamental that correcting it changes everything. Healthy soil is not a medium for delivering chemicals to plant roots. It is a living ecosystem of almost incomprehensible complexity and density. A single teaspoon of healthy, productive soil contains more living organisms than there are people on the entire planet. 100 million to 1 billion bacteria, 25,000 species of fungi, thousands of protozoa and nematodes, all of them interacting, competing, cooperating, and cycling nutrients through a biological infrastructure that took millions of years to evolve. These microbes are the real architects of soil fertility. They secrete polysaccharides and glomalin that bind individual soil particles into stable aggregates, creating the pore spaces necessary for water infiltration and oxygen circulation. They break down organic matter and release nutrients in forms that plant roots can absorb. They fix atmospheric nitrogen. They solubilize phosphorus that is chemically locked in the soil and unavailable to plants. They produce plant growth hormones. They suppress pathogens through competitive exclusion. The plant does not feed itself from the soil. The plant feeds itself through the soil microbiome. It is a trading relationship. The plant provides sugar through its root exudates. The microbes provide minerals and protection in return. When industrial agriculture applies high-dose synthetic fertilizers, it essentially force-feeds plants direct ionic salts, bypassing this relationship entirely. The plant senses that it no longer needs the microbes and stops producing root exudates. The microbial community starves. The biological infrastructure collapses. The soil structure degrades. Water holding capacity drops. The plant becomes 100% dependent on the next dose of synthetic fertilizer to survive. This is what agronomists call the chemical dependency trap, and it is not a side effect of industrial fertilization, it is the business model. Every acre of chemically dependent farmland is a recurring customer. Every acre of biologically active soil managed with living inputs is a farm that is becoming more self-sufficient every season. The $1 liquid does not feed the plant, it feeds the microbes that feed the plant. And that distinction is the entire difference between a system that degrades over time and a system that improves. Lactic acid bacteria are not exotic organisms. They are everywhere, on every plant surface, in the air around you, in the digestive tract of every living animal, in the soil beneath your feet. They are among the most ancient and most successful life forms on Earth. In the soil, they function as what Korean natural farming practitioners call the bouncer, the microbial firewall that determines what lives and what dies in the biological community. Here is the mechanism. When lactic acid bacteria are introduced into the soil in high concentrations, they immediately begin fermenting available carbohydrates, producing lactic acid as a primary metabolic byproduct. That lactic acid lowers the localized pH of the soil environment, and that pH drop is lethal to a specific category of organisms: pathogenic fungi, fusarium, pythium, phytophthora. The organisms responsible for root rot, damping off, and the soil-borne diseases that destroy crops and force farmers into fungicide dependency. These pathogens are pH sensitive. They cannot compete in the acidic environment that lactic acid bacteria create. But the pH effect is only the beginning. Lactic acid bacteria also produce secondary metabolites called bacteriocins, proteinaceous toxins that specifically target and inhibit competing bacterial strains. Combined with the secretion of hydrogen peroxide, these compounds create a chemical environment that is actively hostile to pathogens, while remaining completely benign to the beneficial organisms that drive soil fertility. This is competitive exclusion, not the killing of pathogens with a broad-spectrum chemical weapon that destroys everything indiscriminately. The strategic occupation of ecological niches by beneficial organisms that outcompete pathogens for resources, space, and chemical territory. A 2025 review published in the journal Sustainability documented LAB treatment increasing tomato yield by 15.3% and reducing bacterial wilt by 61.1%. Other horticultural cases in the same review reported over 50% disease suppression, not from a fungicide, from a living biological system that cost nothing to produce. But the most remarkable function of lactic acid bacteria in soil is what they do to nutrients that are already there. In many industrial agricultural fields, there is an abundance of phosphorus in the soil. It has been applied for decades, but it is chemically bound to minerals and completely unavailable to plants. This is nutrient lockup, and it is why a $300 fertilizer application often yields diminishing returns. The plant cannot access what is already there. Lactic acid bacteria produce phosphatase enzymes and organic acids that solubilize these insoluble phosphorus reserves, converting them into orthophosphate ions that plant roots can directly absorb. They produce siderophores that bind and transport iron. They secrete cellulases and proteases that accelerate the decomposition of organic matter, releasing nitrogen, phosphorus, and potassium from crop residues at rates that dwarf what happens in untreated soil. A peer-reviewed study published in the journal Sustainability in 2021 measured the effect of 3-day fermented rice wash water on soil biology. The results were unambiguous. Nitrogen fixation increased by up to 83%, phosphorus solubilization increased by up to 84%, potassium solubilization increased by up to 84%, indole acetic acid, a plant growth hormone, increased by up to 85%. These are not marginal improvements, these are transformations, achieved not by adding nutrients from outside the system, but by unlocking the nutrients that were already locked inside it. The $300 fertilizer adds nutrients. The $1 liquid activates the biological machinery that makes nutrients available. Those are not the same thing, and the difference in long-term soil health between those two approaches is the difference between a farm that is improving and a farm that is dying. In the Mongolian Gobi Desert, where extreme wind and minimal rainfall had defeated 3 previous conventional attempts to plant trees, Korean natural farming and LAB-based techniques were applied to a reforestation project. The trees achieved a 97% survival rate and reached heights of 20 feet in less than a decade, in an environment previously considered biologically dead. In Hawaii, degraded fields treated with Korean natural farming inputs showed a 400% increase in soil biological activity within a single growing season. The Haney Soil Health Score, a rigorous laboratory test for soil vitality, reached 25.4, a score that is 45% higher than pristine, undisturbed forest benchmarks. A human-managed biological system had exceeded the fertility of wild nature. A California organic farm eliminated their $8,000 annual fertilizer bill entirely after transitioning to Korean natural farming inputs, including lab serum. A Colorado market garden reduced crop disease by 50%. A Texas homestead transformed dead hardpan soil into productive vegetable beds in 60 days. These are not anecdotes from enthusiasts. They are documented outcomes from farms that made a measurable economic decision and tracked the results. The University of Hawaii's College of Tropical Agriculture and Human Resources conducted controlled trials comparing LAB treatments to conventional methods between 2015 and 2018. Their findings confirmed what traditional farmers had always known: 300% acceleration in organic matter decomposition, microbial populations jumping from roughly 1,000 colony-forming units per milliliter in untreated soil to over 100 million colony-forming units per milliliter within days of LAB application. The soil was not just recovering, it was transforming. The biological infrastructure that chemical farming had spent decades destroying was rebuilding itself in weeks, because the organisms that build it were never gone. They were suppressed, and the lab serum was removing the suppression. Here is the part that the agricultural chemical industry does not want to be this simple. You need rice, you need water, you need milk, you need 2 jars and 7 days. That is the entire input list. Phase 1 is the rice wash fermentation. Take 1 part white rice and 2 parts clean water. Rinse the rice thoroughly, collecting the cloudy, starch-rich wash water in a clean glass jar. Fill the jar to about 2/3 capacity to allow for gas exchange. Cover it with a breathable material, a piece of cloth or paper secured with a rubber band, and place it in a warm, dark location at roughly 20 to 30 degrees Celsius. Leave it for 2 to 3 days. During this time, the starches in the rice water attract indigenous lactic acid bacteria, naturally present in the environment. The liquid will begin to sour. The pH will drop from around 5.5 to approximately 4.25. A white surface mat of yeast and protein will form on top. When you see that mat and smell the sour, yogurt-like fermentation, the first phase is complete. Strain off the bottom liquid, discarding the floating film. This is your fermented rice wash. It already contains billions of lactic acid bacteria per milliliter. Phase 2 is the milk separation. Mix your fermented rice wash with whole milk at a ratio of 1 part rice wash to 2 parts milk. Cover loosely and ferment at room temperature for 3 to 7 more days. The lactic acid bacteria multiply explosively in the lactose-rich milk environment. They produce acid that coagulates the milk proteins, separating the mixture into 3 distinct layers. A floating curd layer of fats and proteins at the top, a clear yellowish liquid in the middle, settled sediment at the bottom. That clear middle layer is the lab serum, billions of active lactic acid bacteria per drop, concentrated, stable, ready to inoculate soil. Strain it carefully. If you are using it within a few days, refrigerate it. If you need to store it longer, add an equal weight of brown sugar or molasses. The high osmotic environment puts the bacteria into dormancy, allowing room temperature storage for up to 6 months. To apply, dilute at 1 part serum to 1,000 parts non-chlorinated water. 1 milliliter per litre, approximately 1 tablespoon per gallon. Apply as a soil drench at the base of plants or as a foliar spray in the early morning. The University of Hawaii Extension Service confirmed this dilution rate in their published guidelines. $1 of rice produces enough concentrate to treat an entire acre of farmland at the standard application rate, the same acre that a commercial microbial inoculant would cost $200 to treat, the same acre that a chemical fertilizer program would cost $150 to $300 per season. The cost comparison is not close. It is not even in the same category. If this system is this effective and this cheap, the question that demands an answer is obvious. Why have you never heard of it? The answer is not complicated. It is just uncomfortable. The global fertilizer industry represents $250 billion in annual sales. The commercial soil amendment market adds another $45 billion. Every farmer making Lab-E serum in their kitchen is a farmer who has permanently exited both markets. Not just for one season, forever. Because once the biological infrastructure of the soil is restored, it maintains itself. The system becomes self-reinforcing. The need for external inputs diminishes every year. A solution that costs $1 and eliminates the need for hundreds of dollars in annual purchases is not a product. It cannot be patented. It cannot be marketed. It cannot be sold through distribution networks or promoted through agricultural extension services funded by chemical company grants. It is rice water, milk. The intellectual property belongs to a Chinese farmer who has been dead for 9,000 years. Agricultural extension services, often funded by chemical companies, promoted only synthetic solutions while dismissing traditional methods. University agriculture programs, dependent on corporate research grants, followed similar patterns. Regulatory frameworks required expensive EPA registration for microbial products, a process impossible for a method made in home kitchens. Insurance policies quietly voided coverage for farms using non-approved methods. Chohan Kyu, the Korean natural farming pioneer who systematized and documented these methods in the 1960s and 70s, was incarcerated on multiple occasions by the South Korean government under pressure from agricultural corporations that viewed his low-cost, self-sufficient model as a direct threat to their market share. He was beaten, he was surveilled, he continued teaching. By 1995, he had founded the Natural Farming Life School, which has since trained over 18,000 people globally. South Korea now officially recognizes Korean natural farming in national agricultural policy. The Philippines Department of Agriculture actively promotes LAB serum to smallholder farmers. Hawaii's State Extension Service teaches LAB production in official workshops. The knowledge survived the same way it always survives. Because once you understand the biology, the ecosystem builds itself. You cannot unlearn it, you cannot uninvent it, and no amount of institutional silence can make the nitrogen cycle stop working. Let us be precise about the numbers, because the economic argument for LAB serum is not just compelling, it is disruptive. A few cups of rice cost less than $1. That rice produces approximately 5 gallons of lab concentrate. At the standard 1 to 1,000 dilution rate, 5 gallons of concentrate treats over 1 acre of farmland. The only other inputs are water and milk, both of which are available in any household. Compare that to the alternatives. Commercial microbial inoculants, products containing Penibacillus, trichoderma or other beneficial organisms, cost $50 to $300 per acre per application. And their effectiveness wanes after application because the organisms are not adapted to the specific conditions of your soil. They are generic. They are not indigenous. Chemical fertilizer programs for a single acre run $150 to $300 per season, and they do not restore biological function. They replace it with a chemical substitute that degrades the biological infrastructure further with each application, requiring more fertilizer the following season to achieve the same yield. The lab serum costs $1. It restores the biological infrastructure that makes all other nutrients available. It improves with each application as the microbial community it establishes becomes more diverse and more resilient. And it can be rebrewed indefinitely from the same starter culture, meaning the $1 investment is not a recurring cost. It is a one-time entry fee into a self-sustaining biological system. Between 2021 and 2022, the price of anhydrous ammonia, a standard synthetic nitrogen source, increased from $788 per tonne to over $1,300 per tonne, a 67% spike in a single year. For a commercial corn farmer, that translated to an increase from $67 per acre to $132 per acre for a single nutrient alone. The farmer running a lab-based biological system paid nothing for that input, because the nitrogen in a biologically active soil is fixed from the atmosphere by free-living bacteria that the LAB serum had helped establish and protect. The supply chain disruption that devastated chemically dependent farms was invisible to the farm that had rebuilt its biological infrastructure. This is not just an agricultural argument, it is a food security argument, a supply chain resilience argument, a sovereignty argument. The farm that grows its fertility in a kitchen jar is not vulnerable to commodity price spikes, shipping disruptions, or geopolitical events that affect the global fertilizer supply. It is self-sufficient in the most fundamental sense. There is a philosophical thread that connects the ancient Chinese fish farmer who wrote the Yang Yu Jing to the Korean natural farmer who spent decades in and out of prison for teaching people to make fertilizer from rice water. Both of them understood that the most powerful force in agriculture is not the input you add. It is the biological system you cultivate. Fan Li did not add nutrients to his pond. He created conditions in which the biological community of the pond could generate its own fertility. The ducks produced nitrogen. The nitrogen fed algae. The algae fed zooplankton. The zooplankton fed fish. The fish fed families. The system was self-reinforcing. The longer it ran, the more productive it became. Cho Han-kyu did not add nutrients to his soil. He introduced the biological community that could generate its own fertility. The lactic acid bacteria suppressed pathogens. The suppression of pathogens allowed beneficial organisms to establish. The beneficial organisms decomposed organic matter. The decomposition released nutrients. The nutrients fed plants. The plants fed people. The system was self-reinforcing. The longer it ran, the more productive it became. The industrial fertilizer model is the opposite of this. It is a system that requires continuous external input to maintain function. Remove the input and the system collapses. Because the biological infrastructure that would allow the soil to generate its own fertility has been destroyed by the very inputs that replaced it. The lab serum is not a product. It is a key that unlocks the biological potential that was always in the soil, waiting for the conditions that would allow it to express itself. Cho Han-kyu famously stated that the goal of farming is not merely the growing of crops, but the cultivation and perfection of human beings. When we stop trying to bypass nature with chemicals and start working with the microbes of the air, we do not just revive our soil, we reclaim our place in the living world. The power to restore the earth is not hidden in a corporate laboratory. It is hidden in a simple jar of rice water and milk, waiting to be unlocked by anyone with the patience to observe and the courage to ferment. Your $300 fertilizer is treating a symptom. The $1 liquid is restoring the system. $1 of rice, a jar of milk, 7 days, and a biological engine that has been running continuously for 9,000 years, suppressing pathogens, unlocking nutrients, rebuilding soil structure, and feeding civilizations without a single synthetic input. The knowledge was not lost. It was buried under $250 billion in annual fertilizer sales. But every jar of rice water fermenting on a kitchen counter is proof that soil can heal itself, that life creates life, that the earth remembers what we forgot. The lactic acid bacteria are in the air around you right now. They are on every plant surface. They are in the soil beneath your feet. They have been waiting for the entire history of industrial agriculture for someone to give them the conditions they need to do what they have always done. A jar, some rice, a little milk, 7 days. That is the entire distance between a dead soil and a living one. Subscribe. Every week we uncover the biological systems, the ancient methods, and the forgotten agricultural knowledge that the industrial food chain buried, not because it stopped working, but because it could not be sold. The rice is in your kitchen. The bacteria are in the air. The only thing missing is the jar.